I would like to thank all of you as well. I'm very honored to be here today. I get to present today the good news. I get to talk about data interoperability and in its aspects of being able to save lives. I feel very fortunate. This is actually my third young researcher talk that I've given, just since June 1st. So the third one this summer. The first one was 50 students, and actually is going to be mostly what I'm going to be talking about was the preparation to get ready for a summer institute where we had 50 international students. There was another one that I did at the National Science Foundation where there were 100 young researchers who submitted white papers. And the funny thing is there's been a little bit of overlap between these three different workshops, though no single student has been at all three. And I've had to actually create three different talks, substantially different talks. But I tell you what, with the overlap and the smallness of this community, I don't want to do any more because I think people will just say, not her again. So I get to talk about the good news, not the sinister ones and the privacy, but I have to agree that it really truly is the triangulation of data that's really the really interesting type of research that's taking place today. It may offer the most ability for us to violate each other's privacy, but it's also a way in which we can save lives. I'm really quite fortunate because I work in a research laboratory where one of our mission statements is to bring computer science, core computer science, to work on the world's most challenging problems. And I feel very fortunate to be able to do that. So these are just some of the research areas that we do inside of Microsoft Research. And when Tony and I were formulating the fourth paradigm, we had a very hard time. This was just 6 years ago. We had to sort of handpick and go out and look for multidisciplinary research. But today, I mean, at this NSF conference, every single one of the 100 students presented a poster that was multidisciplinary. And I've looked at the posters out here and looked through the different young researchers, and I can see that multidisciplinary research is an idea that's time has come. So the research that I'm going to talk about is a project where we're trying to set up something that I like to refer to as the virtuous circle of research, where researchers go out, they collect data, they gather it, or they use devices to do that. With the Internet of Things, we're seeing more and more devices out in the wild that actually collect the data that then can be put up into the cloud so that geographically dispersed teams can actually work together to solve very difficult problems or monitor different processes. Should a situation occur that requires some kind of action, that can then be done cross-functionally, and then corrective action taken, which in turn drives more research. So this is the kind of thing that we're trying to set up with this program. And the case study I'm going to use is I'm going to use water. We all think of water as the bringer of life. We can't survive without it. There's not enough fresh water. It's definitely one of these resources that perhaps even will be more critical to conflicts and things like that around the world than even oil. So it is the bringer of life, but it is also, at least in the United States, it is the bringer of death. Flooding causes more deaths, no matter how it occurs, whether it's tsunamis, superstorms, or flash floods. It causes more deaths in the United States than any other type of natural disaster on its own. And as a result, it's created financial problems for our country. I was actually in Texas meeting with my collaborator down there, David Maidment, and we were talking to the Texas Water Quality Board about drought. They were claiming that there's no such thing as climate change. And while we were there, we met during the day, and several of these representatives, the politicians, came out with us with dinner. And as we were going out, we actually noticed that it was starting to drizzle, which in a way, in my mind, I thought, this is a bad thing because they're going to be convinced that I'm wrong. But come to find out the next morning that a flood had occurred overnight. Onion Creek flood is what it was referred to. And what happened is an upstream water shed from the city of Austin, during Austin city limits, I might add, had flooded overnight. There was a stream gauge, and it indicated a problem, and first responders were mobilized. But unfortunately, what happened is it stopped working because it was inundated. And this isn't uncommon. Flooding for flash floods actually can go up and drop to zero. That's not unexpected. So what happened is these first responders went home. As a result, they were unable to respond to people in need. 5 people died. 700 homes were actually flooded. But then there was this year. So in Oklahoma and Texas this year and in Austin, not only did dozens of people die, but in addition to that, we lost 2 first responders, and this is our first line of defense when it comes to us protecting the lives and livelihoods of our population. So yeah, that was May 27th and 29th. So this is my collaborator, David Maidment. Marcelo Somas is a postdoc in his laboratory. He was also my visiting researcher at Microsoft Research. Fernando Salas was my intern for last year. But really, David is the star of this show because he was able to bring together industry, he was able to bring together consortia and standards bodies, he was able to bring together multiple universities to collaborate together on government data as part of our nation's Open Data Initiative and the Department of Interior's Open Water Initiative. So he was able to bring all these people together for us to be able to collaborate on it. The goals of it is to carry out this nationwide scale, time-sensitive hydrological modeling so that we can actually know when we're actually in a situation of danger. That improves emergency response. But additionally, it can improve research processes that don't work just for drought, but for other types of natural disasters, and could lead to sustained engineering in research, in academia, and in industry. So why flooding, and why would Microsoft even care about this? Well, right now our country is more than $30 billion in debt thanks to Superstorm Sandy and Hurricane Katrina. On average, we earn more than $8 billion. It costs us more than $8 billion per year, but this number was succeeded in May by quite a large amount, and it's now only August, and we're already past that for this year. But for inside of the company, it was an opportunity. A lot of times product teams are a little bit removed from real data interoperability problems, and so it was an opportunity to show them that this is how data works in the wild, how dirty and messy and sometimes dangerous it is to collect the data, and be able to prioritize the work that they do as they start to release their products. And so we actually had a great feedback loop. The researchers themselves who collaborated with us were using technologies that have not even yet been released. And we were able to get the product team to prioritize some of their work. So that was valuable to me also as a researcher. But I think really ultimately it was because there was so much skin in the game by so many people who were so motivated to make a difference. So the problem really is in the United States is that each of our agencies has a responsibility for having their own open data with taxpayer generated information, and they share it. But the problem is they're not actually allowed to share it with one another. Each agency isn't allowed to carry and share their other data. So it really takes bringing together something like this group of collaborators in order to address the problem of doing predictive analytics for flooding. So USGS does historical data. This is the temporal aspects of it. The Army Corps of Engineers collects our reservoir data, which can highly impact the situation in flooding. And then the National Weather Service is the one who actually predicts the weather going forward. So we have both historical and future data involved with this. This then lays over the FEMA flood mapping information, and that tells us where danger spots are. The challenge really was to bring all of this different data together, put it into a database, do spatial and temporal aggregation, and then be able to serve it up as a web service in the cloud. And we started out, so Marcelo, he actually did the Eastern Seaboard. We piloted so you could do the end-to-end system just using one of the 13 water regions in the United States. While Fernando worked on the Gulf region, mainly because this is the place that more death occurs in the United States than any other region, any other water region. So we worked to just pilot these 2 areas. We accomplished that at the end of the visiting researchership and internship. And then what we wanted to do is we wanted to scale that up to the whole nation for all 3 million river reaches across our country. And we have the kind of weather that ranges all the way from Arctic to tropical. So this is another challenge. And we have extreme geospatial problems. But the ultimate goal was to create this Young Researcher Institute at the National Water Center, where we would bring these 50 students to take the data product that we had generated and do some very cool research and applications on top of it. That was the goal. And they lived in residence for 7 weeks, and then at the end of that 7 weeks, mid-July, I think it was actually July 17th, they all presented the research that they had done collaboratively as a group together. So I mentioned already that there's a lot of aspects to this, the geospatial aspects of it. But what we did is we actually put a lot of the National Weather Service data, we regridded the data from the National Center for Atmospheric Research that actually grids that down to the individual stream level. And then we used a localized forecast system that was developed by a researcher at JPL to then add that with the Army Corps of Engineers information, run that in Azure, do predictive analytics on Azure ML, and that's where we stopped, actually, to be perfectly honest with you. We didn't get any further than the data interruptibility. We hope to go to notification because my phone knows where I live. My phone tells me how I get there. It can warn me if my house is in danger, whether the pathway I would take to get home in a disaster situation, whether or not that's a direction I should go. So that's what we hope to actually accomplish in the next year. That's future work. And just to kind of give you an overview of a very quick experiment, this was one of the student projects. I'm showing you, there's 3 stream gauges. This is actually a river that I grew up next to in Idaho, believe it or not. The red line is the one we're going to pretend is taken out. So remember at Onion Creek, we had a stream gauge that failed. So what we have there is all the other streams are either positively or negatively correlated in some way with it. And what we wanted to do was I'm only showing 3, one that's positive and one that's negative, but there are hundreds of river reaches on the Boise River. But just by example, I wanted to let you know that it's not just positively correlated ones that we selected all of the river reaches that were relevant. And what we did is we actually took that, we put it in Azure ML. We allowed the student to use their own standard R programming, as you can see from the right-hand side, that Python and R are first-class citizens inside of Azure ML. But we ended up using an off-the-shelf boosted decision tree, and that gave us the best results. And it was very simple to do this. This is a reproducible thing. We just dragged and dropped any statistical or machine learning model over here. The goal of this is to help somebody like Tim Petty, the student who was involved with this, who's a hydrologist, not have to know about machine learning to do some interesting research. And this is the result. We got a very high correlation between the stream gauge and that with a student who'd never done machine learning in their life. So the ultimate goal was really to bring together open data and do interoperability and enable us for our public safety to be more proactive than reactive. And with that, I'll take questions.
Okay, there's a question there.
So actually now in Puerto Rico, we have kind of like the opposite problem, that we have the worst drought in our history. Is there any way that you think that data and gathering information could be helpful in just, this other extreme case?
Yes, actually. In fact, if I'm not mistaken, I can show you an example. I swear, this was a slide I had pulled out into the appendix because I didn't have that time. I didn't think I was going to have time to get to show it. But yes, this is an example of something that's run on NLDAS, which is a standard data set that we have. A student literally performed that very quickly. And remember, when I originally started this conversation, we were working on this problem. And that's why I took it out. I had it in there because I was going to tell you where we started. But the reality is that this is you can go to this website down below and take a look at that, and you'll have an opportunity to see this is a student. He's a PhD student actually at University of Texas at Austin, and this is his work as well, Gonzalo. So please take a look at that. I think that when I said that we want to make sure that whatever we develop is something that's reproducible and can work for other disaster situations, this is actually what I was referring to. The reason why I had this slide in here was actually a different reason, which is uncertainty. This shows very easily the uncertainty involved in the prediction, and I think that's extremely important because sometimes our policymakers don't understand, and definitely the public doesn't understand. When you tell them there's a disaster, if you don't tell them what the likelihood of that disaster is, you're doing them a disservice.
Any other question?
So I wondered, actually, when you mentioned the fact that those agencies weren't allowed to share data with each other, how you ended up getting around that. It seems like you were able to use that data and make useful results with it, but then it seems like you weren't allowed to do that, at least at first.
Oh, right, I'm sorry. Let me clarify. Thank you for asking. The fact is, they can't share. But it's all open and available. There's nothing that stops me as a US citizen to going out and downloading that data. In fact, there's nothing that stops you either, or anybody else in this room, because it's open data. So we can all pull that down. It's just that normally when you see something, a project of this scale, it's done at the governmental level. But it was that consortium of folks that really allowed us to interoperate that data, and we're hosting it in Azure, so it's not a problem for the US government if we do it for them.
Sorry, just one question myself, along with what he was saying. You are talking about interoperability, so combining different sets of data, and this reminds me of, de-anonymization, for example. That is, by combining different sets of data, you manage to get information that no one alone will reveal you. So how much open data is enough from your point of view? That is, would you advocate for combining everything with everything, opening everything, or is there a certain point in which then there are risks of knowing too much, let's say, by combining them?
The way I would describe this is that it's like, the Hippocratic Oath, do no evil. Like, I really think that's the important thing to consider with data. I think that, in particular, data that has been collected by researchers should be made available openly. I think data products like this one should be made available openly. I worry when these things actually get hidden, because I think that actually does us a disservice. That is something that would be a risk if a company gets involved and there's some intellectual property involved with it. I think that's a risk. But I've been very fortunate. I work in a place where it's open data, Creative Commons, open publishing, and so I have an advantage there. But I think that also colors my opinion, that I think that more data, not less data, should be available.
Okay, so there was one question there.
Yeah, so it seems that what you were doing was collecting all this data is very, very interesting. And I guess that's more or less the goal of the project. But the problem, like the original motivating problem, it's like a very low likelihood event with extremely high damage.
Yes.
Right? So those are inherently very difficult to predict. So do you have did you get any insight on these kind of events when you were collecting all this data?
Thank you for asking that question. Yes. If I didn't believe that we were experiencing climate change before, I know that we are now. These students, by looking at these data products, discovered that if they looked back 10 years or more, it reduced their predictive ability for the experiments that they ran. So let me say that the opposite way. If they used data from the last 5 years, they were more successful in doing predictive analytics than they were if they included any data prior to 5 years. We are living in a changing world. So if that probably, for me, is one of the greatest insights that I think came out of it, was the fact that now, it was very obvious. That was an excellent question.
So now you have mentioned that your predictions get much better if you pick up the last 5 years. I have two questions, actually. The first is, how many data points do you have in your analysis? Because, is 5 years a relevant period? Climate change is a fact. I'm not arguing
I
for
understand.
that, but I'm just talking about the statistical point. And then my second question would be, were there any monitoring errors in the data? Did you have to deal with data cleaning? Thank you.
So the data points for this particular data set, coming from the 3 different disparate data sets that we combined together in conjunction with the model that we ran, it's every 15 minutes we get information of every day, of every hour for the whole year. So a lot. And then the reservoir data is reported either on a 1 or a 2 hour tweet. The National Weather Service data is continuous. So to be perfectly honest with you, we have a lot of data. And even to run the model, which when we first tried to run it, we couldn't. We were using the University of Texas's, they call it TAC. We weren't able to run it properly. It took a very long time, so it wasn't even real time. When we moved it up into the cloud, we used the largest type of cloud configuration that exists today. Very expensive, but we were able to run this model in 15 minutes. But think about that. That tells you how much data that we used in order to create these calculations. So a lot of data. And the answer to the question about cleaning, this is near and dear to my heart. Remember I said it was dirty, dangerous, hard work to do the data part. the statistics at the end are at the end. The hard part actually is at the collection. There were a ton of missing values, sometimes on, sometimes off, just like the Onion Creek flood. And this is why it's so important to do the interpolation experiment to see if you can actually estimate for when values are missing. We do find that some of the data either over or under reports, but one of the other things that we were able to do through the experiment was students were able to locate those types of information. So this was the thing, it just turned these young researchers' minds loose to find those particular problems. So it was a great opportunity, yeah.
Okay, thanks a lot, Christine. And let's move to the next speaker, Alessandro Acquisti.